Okay, hello students. So last time we discussed about the wave equation, electromagnetic wave propagation in different type of medium, and in last lecture we derived wave equation. So wave equation for electric field and wave equation for magnetic field, and here we assume that electric field in x direction, magnetic field in y direction, and the propagation direction is z direction. Okay, so in last lecture we derived this equation for electric field. It is E of zt is equals to E0 e raised to minus alpha z e raised to j omega t minus beta z into ax. Similarly, for magnetic field, H vector of zt is equals to H0 e raised to minus alpha z e raised to j omega t minus beta z a by. Okay, so here we assume that electric field is present in x direction, magnetic field in the y direction, and this z is indicate it is a propagation direction, and the propagation direction is always z. Okay, here it is omega t minus beta z, means the propagation in positive z direction. Suppose the propagation direction is negative z direction, so in that case it is omega t plus beta z. Okay, so in last lecture we derived this equation, and we will also discuss about one more important thing which is known as gamma, and it is known as propagation constant, and gamma is nothing but it is j omega mu sigma plus j omega epsilon. Okay, where sigma is conductivity. Okay, here sigma is known as conductivity, epsilon is permittivity, and mu is permeability. Okay, so and if you have to solve, okay, it is in under root. Okay, under root of j omega mu sigma plus j omega epsilon. And if you solve this equation using Taylor series expansion method, so it has a two solution. First is real solution and second is imaginary solution. So it is alpha plus j beta. Okay, we will also discuss about what is alpha, what is beta, and what is gamma. So here alpha is known as attenuation constant. Alpha is attenuation constant, beta is known as phase constant. Okay, and gamma is known as propagation constant. Okay, so in last lecture we have discussed about all those things, gamma, alpha, and beta. Okay, so now in today's lecture we'll discuss about the more important thing which is known as intrinsic impedance. Okay, so first of all we will discuss about what is intrinsic impedance. Okay, so in a general case, if we discuss about voltage and current, okay, so V is known as voltage and I is known as current. Okay, so what is the relationship between V and I? We know that V is equals to I into R. Okay, where R is known as resistance. R is known as the resistance. Okay, but if in any circuit, if resistors, inductor, and capacitor are present, okay, so overall combination is known as impedance. So we can write in this case V is equals to I into Z, where Z is known as impedance. Okay, so there is a small relationship between voltage and current, but here we have to relate it with our electromagnetic wave. Okay, so here we can write V. Okay, so first of all, what is the unit of V? V is nothing but it's a simple volt. What is the unit of I? I is current, which is ampere. And what is the unit of Z? Z is ohm. Okay, so in short we can say that volt is equals to ampere into ohm. Okay, so now again I have to write the same thing here. Volt is equals to ampere into ohm. Okay, now I have to divide it right hand side and left hand side with meter and meter. Okay, so volt by meter. Okay, so we know that it is nothing but volt by meter. It is a unit of electric field intensity. Ampere by meter, it is a unit of magnetic field intensity. And this ohm is nothing but my intrinsic impedance. Okay, so in a short way we can write that E is equals to H into N. Okay, in a circuit it is V is equals to IR or V is equals to IZ, but in terms of electromagnetic wave, it is E is equals to H into N. E is electric field intensity, H is magnetic field intensity. So the question is, what is N? N is known as intrinsic impedance. N is known as intrinsic impedance of medium. Intrinsic impedance of different medium or different material. Okay, so in today's lecture we will derive the equation of intrinsic impedance. What is intrinsic impedance exactly? Okay, so now to derive intrinsic impedance, okay, so in last lecture we have to do some assumptions, okay, and we use our Maxwell equation in point form also. Okay, so we have total two. Okay, we use two Maxwell equation in point form. First Maxwell equation is del cross E is equals to minus del B by del T, but B is equals to mu H, so this minus mu del H by del T. And second Maxwell equation that we have used is del cross H is equals to conduction current density plus displacement current density. Conduction current density is sigma E and displacement current density is del D by del T. Again, I have to modify it, sigma E. D means epsilon E, so this epsilon del E by del T. Okay, so in last lecture we used these two Maxwell equation to derive this wave equation. Okay, now we use the first Maxwell equation, means this equation, to derive the equation for intrinsic impedance. Okay, so we use this equation to derive the equation for intrinsic impedance. Okay. So here I have to again write it. So del cross E is equals to minus del B by del T, or you may write del cross E is equals to minus mu del H by del T. Okay, now if you notice here, I have to take the partial derivative of magnetic field with respect to time t. Okay, and in last lecture we assumed one more thing, that our assumptions is that in our last lecture that H of t, we know that electromagnetic field is a function of space and time. Okay, so H of t is equals to H0 e raised to j omega t. If I have to do the partial derivative, del H by del T is equals to H0 j omega e raised to j omega t. Okay, I have to rearrange this term H0 e raised to j omega t into j omega. Okay, so this term is nothing but my H of t. Okay, so I have to simply write H, or you may write H of t. I have to write simple H, so this j omega into H. Okay, so now I have to substitute this value into this equation. Okay, so del cross E is equals to minus j omega mu H. Okay, so what is H? H is equals to del cross E divided by minus j omega mu. Okay, now here one more thing is, up to this, okay, we have to consider electric field is present in x direction, magnetic field is present in the y direction, and the propagation direction is z direction. Okay, again we'll quickly revise it. So here we consider there are the three axes. Okay, this one is my x axis, y axis, and z axis. Okay, then what we have consider, we consider that it is the electric field which is present in the x direction. Then this one is my magnetic field which is present in y direction. Okay, and which one is the propagation direction? The propagation direction is z direction. Okay, so this one is my electric field, magnetic field. Okay, so this is a simple representation of my electromagnetic field propagation. Okay, so here we assume electric field in x direction. Okay, so you may write here is Ex, magnetic field in the y direction, so it is Hy, and the propagation direction is, it is z direction. Okay, so now here we consider it is not only E. Okay, it is Ex. Similarly, it's not only H, but it is Hy. Okay, you can write in this way. Okay, now we have to solve this one. What is del cross Ex? Okay, so del cross E is equals to, okay, we can solve any cross product using matrix determinant method. Okay, so it is Ax, and we consider Cartesian coordinate system xyz, del by del x, del by del y, del by del z. Okay, now what is E? E is present in which direction? In x direction only. Is absent in y direction, is absent in z direction. Okay, z is the propagation direction, that means E is traveling in z direction, but E is present in only positive x and negative x direction. Okay, so here only which component is present? X component is present. Ey is 0, Ez is 0. Okay, now if you do the simple determinant, okay, so we will get here it is a del Ex by del z, then plus Az. Okay, I will just simple find out its determinant. Okay, del, okay, it is Ex by del y. Okay, but out of these two, which one is a valid? This one is a valid. Why? This one is invalid. Why? Because electric field is present in x direction, magnetic field is present in the y direction, and the propagation direction is z. Okay, and what is z? Z is nothing but my space quantity. Z is known as my space quantity. Okay, so electric field is vary with respect to time and space only, and here we consider z is space quantity. Okay, so here if you have to do the partial derivative with respect to this y, so answer is 0. So only this term is present. Okay, so here final answer is del Ex by del z into Ay. Okay, so we consider only this term here, and so it is Hy is equals to this del cross E. Del cross E is del Ex by del z divided by minus j omega mu. Okay, now the question is where is Ay? Okay, but if you notice this Ay direction and the direction of Hy, okay, direction of Hy is the same in the Ay. Okay, here it is Ay, so Ay cancel out. Okay, so Hy is equals to this one. Now one more thing, again here we have to take the partial derivative of Ex with respect to z. Okay, so now one more thing is, we know that in the last lecture we assume one thing, electric field change with respect to z. E of z is E0 e raised to minus gamma z, where gamma is propagation constant. Okay, so if you have to take the partial derivative, so it is E0 minus gamma e raised to minus gamma z. Okay, so you can write it as minus gamma e. Okay, so I can write Hy is equals to minus gamma e upon, okay, you may write here it is Ex, so this Ex upon minus j omega mu, so this minus terms are cancel out, so gamma Ex upon j omega mu. Okay, well, so finally my equation Ex by Hy is equals to Ex by Hy is equals to j omega mu divided by gamma. Okay, and we know that what is E by H? Okay, we know that E is equals to H into gamma. Okay, from V is equals to IR, so E is equals to H into, not gamma, eta, intrinsic impedance. Okay, so what is E by H? E by H is intrinsic impedance eta. Okay, so it is nothing but eta is equals to j omega mu divided by gamma. So eta is equals to j omega mu divided by gamma is under root of j omega mu sigma plus j omega epsilon. Okay, so I have to simplify it. So my final equation is eta is equals to j omega mu sigma plus j omega epsilon. Okay, so this one is the last and final equation of intrinsic impedance. Okay, so here you have to notice that this intrinsic impedance has also two part, real part and imaginary part. Okay, and it is also has angle. If I write in a polar form, so it has some angle. Okay, so if I write in terms of mode, so we can write in terms of mode of n is equals to it has a real part and imaginary part also. Okay, so it is mode, so it's under root of omega mu upon under root of sigma square plus omega square plus epsilon square likewise. Okay, we cannot write in this way, but ultimately we can say that this intrinsic impedance has a two part. First is real part and imaginary part, so some angle is present. Okay, some angle is present. Okay, so eta is known as intrinsic impedance of medium. Okay, and we have total four type of medium. Which are the four type of medium that we have discussed in last lecture? We have total four medium. First medium is my free space, or you can say that it is air. My second medium, okay, first medium, again I will repeat, first medium is my free space. Okay, which one is the second medium? The second medium is lossless dielectric medium. Lossless dielectric medium. Which one is the third medium? Third medium is my lossy dielectric medium. And number 4 is good conductor. Okay, now each and every medium has a property, okay, that we have discussed in last lecture. So we will quickly revise it. Free space, so free space has conductivity 0, epsilon is equals to epsilon 0, mu is equals to mu 0. What about the lossless dielectric medium? Sigma is equals to 0, conductivity is 0, epsilon is equals to epsilon 0, epsilon r, mu is equals to mu 0, mu r. What about the lossy dielectric medium? Lossy means conductivity is not equal to 0, epsilon is same, epsilon 0, epsilon r, mu is equals to mu 0, mu r. And what about the good conductor? Good conductor means very, very higher loss. Okay, that means if conductivity is infinity, is approximately infinity, and epsilon is equals to epsilon 0, epsilon r, and mu is equals to mu 0, mu r. Okay, so now in today's class we discuss about the electromagnetic wave propagation in free space first, then lossless dielectric medium, then lossy dielectric medium, and finally good conductor. Okay, so let us start with first free space. Okay, so the question may be asked in this way in exam question. Okay, first explain electromagnetic wave propagation in free space. Okay, so first we know that these are the property of the free space. Okay, so first is explain electromagnetic wave propagation in free space. Okay, so we have to write first of all the property of the free space. Conductivity is 0, epsilon is equals to epsilon 0, mu is equals to mu 0. Okay, now we have to write our equation for electric field and magnetic field, okay, which is a function of space and time. Okay, so here E of ZT and H of ZT, we know that E of ZT is E0 e raised to minus alpha z e raised to j omega t minus beta z into ax. What about H of ZT? H0 e raised to minus alpha z e raised to j omega t minus beta z into ay. Then we write equation for intrinsic impedance and propagation constant. Okay, so first I will take propagation constant. Okay, so propagation constant gamma is equals to under root of j omega mu sigma plus j omega epsilon. Okay, remember one thing, if any theory is asked in the exam, either it is free space, lossless dielectric, lossy dielectric, or it may be a good conductor, we always write in this way. First we write the property of the medium, then we write these two equations, then after we write the propagation constant equation, and finally we write the intrinsic impedance equation. Okay, so now by the property of the free space, sigma is equals to, or conductivity is equals to 0, epsilon is equals to epsilon 0, mu is equals to mu 0. I have to put all this value in my equation. Okay, so now it is j omega, now mu is mu 0, sigma is 0, so 0 plus j omega 0, so this is j omega epsilon 0. Okay, so it is j square omega square mu 0 epsilon 0. I have to remove it from the square root. Okay, so gamma is equals to j omega under root of mu 0 epsilon 0. Okay, so this propagation constant has only which part? Imaginary part. Okay, so real part is totally 0. So I have to compare it with alpha plus j beta. Okay, so here we can say that if I have to compare it, so alpha is equals to 0. Alpha is 0, it indicates attenuation of my electromagnetic wave is 0. Attenuation is 0, that means the amplitude of, okay, or maximum value of electromagnetic wave remains constant throughout the free space. Okay, that means attenuation is 0. Okay, and again next, beta is equals to omega under root of mu 0 epsilon 0. What is beta? Beta is phase constant. That means we observe some phase difference when electromagnetic wave is propagated in the free space. Slightly phase difference. Okay, not much more than. Okay, but it's slight. Ideally you can consider there is no phase difference. Okay, but actually beta is not phase difference, it's a phase constant. Okay, so beta is equals to omega under root of mu 0 epsilon 0. Okay, so now we have to here more focus on beta. Beta is phase constant. What do you mean by the phase constant? Okay, you have to write all those things in the same theory, which is explain electromagnetic wave propagation in free space. Okay, so now we focus on beta. Beta is phase constant. Okay, so here we finally write beta is equals to omega under root of mu 0 epsilon 0. And now the question is, what is beta? How can we realize beta? Actually phase constant. Okay, so we know that what is the maximum phase difference of any signal. Okay, see here, suppose I will draw any signal. Okay, suppose for example I will draw one signal. For example, this one is my input. Okay, there suppose any type of signal. Okay, don't consider it as a electromagnetic. Okay, you can consider as a electromagnetic wave, you can consider any signal. Okay, and one signal is just overlapped with this original signal. Okay, the second signal is just overlapped with the original signal. So what is the phase difference? The phase difference is totally 0. The phase difference is 0. Okay, next we draw another two signal. Okay, suppose this one is my, for example, my input signal. Okay, and yes, this one is my output signal. Okay, now in this case, what is the phase difference? So here the phase difference is exactly 90 degree. How it is 90 degree? Okay, so we know that here is 0 degree, this one is my 2 pi, means 360 degree, here is pi 180 degree, So this one is exactly pi by 2, 90 degree. Okay, so phase difference between these two signal is 90 degree. Okay, so here what is the wavelength? In this case, wavelength, okay, so this is known as wavelength. So wavelength is denoted as lambda. Okay, so lambda is wavelength. Okay, so for lambda wavelength, the phase is 2 pi. Okay, for lambda wavelength, the phase is 2 pi. The phase difference is 2 pi for the lambda wavelength. Okay, so here we can write in this way. So actually we have to derive what is beta, the equation of beta. Okay, so here we can say that for, okay, so beta, actually we want to derive the equation of beta like this. Beta, actually beta is equals to 2 pi by lambda. Okay, beta is equals to 2 pi by lambda. 2 pi by lambda. Okay, so for lambda wavelength, the maximum phase difference is 2 pi. Okay, so for 2 pi, okay, for maximum phase difference 2 pi, it should be lambda. Okay, so for phase difference beta, okay, for 1 meter, okay, for lambda meter it is 2 pi. So for 1 meter, for lambda meter wavelength, the phase difference is 2 pi. So for 1 meter wavelength, what should be the phase difference? So it is nothing but, this question mark is nothing but beta. So that is why beta is equals to 2 pi by lambda. Okay, so it is 2 pi by lambda. Clear? Okay, so here beta is nothing but my 2 pi by lambda is equals to omega under root of mu 0 epsilon 0. Okay, so I will write the same thing here. So beta means it is 2 pi by lambda is equals to, we know that what is omega. Omega is 2 pi f under root of mu 0 epsilon 0. 2 pi cancel out. Okay, we can write in this way. So it's lambda into f is equals to 1 upon under root of mu 0 epsilon 0. Lambda into f, wavelength into the frequency, it is nothing but velocity. Okay, velocity of light, c is equals to lambda f. Okay, we know that the velocity of light, v or c, is equals to lambda f. Okay, so it is nothing but the velocity of electromagnetic wave in free space. Okay, v is equals to 1 upon under root mu 0 epsilon 0. Okay, now I have to put the value of mu 0 and epsilon 0. Okay, so velocity of electromagnetic wave in free space. What is mu 0? Mu 0 is 4 pi into 10 raised to minus 7. Okay, and what is epsilon 0? Epsilon 0 is 8.854 into 10 raised to minus 12, or it is 10 raised to minus 9 upon 36 pi. Okay, now you can do the calculation by yourself. So you will get answer 3 into 10 raised to 8 meter per second. Okay, so it is nothing but velocity of electromagnetic wave in free space. Okay, so this is the velocity of electromagnetic wave in free space, which is nothing but the same as the velocity of light. Okay, so electromagnetic wave propagated in free space has the same velocity of light. Okay, okay, so we have finished this one. Okay, free space, explain electromagnetic wave propagation in free space. Just first we write these two equations, then okay, propagation constant, I have to compare just with alpha and beta. Value of alpha is 0, attention is 0, then beta. Okay, and we have to derive the whole thing of beta. Now one more thing is left, which is known as intrinsic impedance. Okay, this one, intrinsic impedance of free space. Okay, eta. Okay. So intrinsic impedance is equals to j omega mu upon sigma plus j omega epsilon. Okay, it is known as propagation constant zeta, intrinsic impedance eta. Okay, so again we put this condition. So it is equal to j omega mu 0, sigma is 0, 0 plus j omega epsilon 0. So eta intrinsic impedance eta is j omega cancel out. So this mu 0 epsilon 0 put here 4 pi to times minus 7 10 raised to minus 9 by 36 pi. So answer is 120 pi, or if you put pi is equal to 3.14, so I think it is 377 ohm. Why this ohm? Because the unit of intrinsic impedance. Okay, so actually it is the impedance which is present in free space. For what? For electromagnetic wave. So it is the impedance of air. You can say that it's the impedance of air or the impedance of free space. Okay, it's one kind of resistance. Okay, you cannot measure this resistance using multimeter. Okay, because the multimeter is used to measure the resistance. Okay, it's used to measure the physical value of resistance. Okay, for voltage and current. Okay, it's not a physical resistance. Okay. So eta is equal to 120 pi ohm or 377 ohm, and it is a resistance for electromagnetic wave. It's not a resistance for voltage and current. It's not a resistance for voltage and current, but it's a resistance for electromagnetic wave. Okay, so finally we have finished our question, which is electromagnetic wave propagation in free space. Okay, next, electromagnetic wave propagation in lossless dielectric material. Electromagnetic wave propagation in lossless dielectric material. Okay, now it's very simple. Just we have to modify one more thing. Okay, so number 2, electromagnetic wave propagation. Okay, second question, explain electromagnetic wave propagation in lossless dielectric material. Electromagnetic wave propagation in lossless dielectric material. Which are the property of lossless dielectric material? Conductivity is 0, epsilon is epsilon 0 epsilon r, mu is equals to mu 0 mu r. Okay, now no need to prove all those things. I will just directly write. Okay, so again, what you have to do, first of all you have to write these two equations, then after do the calculation for this propagation constant zeta, and then calculation for intrinsic impedance eta. Okay, so I directly write these things. Okay, so same way here, propagation constant is j omega mu sigma plus j omega epsilon. Okay, I write directly all those. Okay, so again you have to just compare the real part imaginary. Okay, so this j omega mu 0 epsilon 0 mu r and epsilon r. Okay, and compare it with real part and imaginary part. Okay, so again here alpha is equals to 0, attenuation is 0. Okay, and what about the beta? Beta is equals to omega mu 0 epsilon 0 mu r epsilon r. Put beta is equals to 2 pi by lambda. Do all those things. Okay, and finally we conclude that velocity of electromagnetic wave in lossless dielectric medium is 3 into 10 raised to 8 divided by mu r epsilon r meter per second. Okay, so what you observe here, if you just compare these two equations, it is the velocity of electromagnetic wave in free space, but this one is velocity of electromagnetic wave in lossless dielectric material. Okay, so if you compare these two, so velocity of electromagnetic wave in lossless dielectric medium is decreased by amount root of mu r epsilon r. It depends on the permittivity, relative permittivity and relative permeability of medium. Okay, similarly, what about the intrinsic impedance? Okay, for lossless dielectric medium. Okay, so intrinsic impedance eta is equals to, okay, again put this equation, j omega mu sigma plus j omega epsilon under root. Okay, sigma is equals to 0, mu is equals to mu 0, mu r epsilon is equals to epsilon 0 epsilon r. So this 120 pi, or you may write 377 ohm. So this 120 pi under root of mu r by epsilon. Okay, so these are the slight modification of this propagation constant and intrinsic impedance when electromagnetic wave is propagated through the lossless dielectric material. Okay, now next third is lossy dielectric material. Okay, now for lossy dielectric material, if you observe here, sigma conductivity does not equal to 0. That means the material or the medium is lossy medium. Okay, remember one thing, if conductivity is 0, so we can say that it is lossless. Free space is also lossless. This one is lossless. Lossless, that means, what do you mean by the lossless? Lossless means its attenuation is 0. Okay, similarly here, lossless means lossless, its attenuation is 0. Okay, so when sigma is 0, attenuation is 0. Here also sigma is 0, attenuation is 0. Okay, so if no conductivity, it indicates no loss. But if conductivity is present, so loss is present. Okay, more conductivity, more loss. Okay, so for good conductor offers ideally infinity, or you can say that very, very high conductivity. Okay, so more loss in good conductor. Okay, so we can say that which one is a bad medium for electromagnetic wave? Good conductor is a very, very bad medium for electromagnetic wave. Okay, and which one is a ideal, or which one is a good medium for electromagnetic wave? Free space. Free space is a perfect medium for electromagnetic wave propagation. And conductor is very, very bad medium, because conductor has a very, very high conductivity. If conductivity is very, very high, loss is high. Okay, so that is why free space is a ideal or is a good medium for electromagnetic wave propagation. Okay, now we discuss third, lossy dielectric material. Okay, so in lossy dielectric material, here sigma is equals to 0. Sigma is equals to 0, it indicates what? It indicates that the loss sigma does not equal to 0. Sigma does not equal to 0 is indicate is a lossy medium. Okay, so for okay, now we do the calculation for lossy medium. Okay, so number 3, lossy dielectric medium. Lossy dielectric medium. Okay, which are the property for lossy dielectric medium? Sigma does not equal to 0, epsilon is equals to epsilon 0 epsilon r, mu is equals to mu 0 mu r. Okay, so these are the property of the lossy dielectric medium. Okay, now the main thing is, again you have to write all those equations. Okay, electric field equation, okay, electric wave equation, magnetic wave equation, then do the calculation for the propagation constant. Similarly, do the calculation for this intrinsic impedance. Okay, we do all those things, but now the problem is, okay, see here, now the propagation constant is j omega mu sigma plus j omega epsilon. Okay, so here if you notice, sigma is not 0. Okay, now we apply Taylor series expansion method to solve this equation. Okay, we apply the Taylor series expansion method to solve this equation. Okay, and then finally compare real part and imaginary part. Okay, so the equation becomes very large. Okay, and it's a time consuming equation. Okay, so after completing this lecture, okay, again we will touch this topic, electromagnetic wave propagation in lossy dielectric material. Okay, because it takes long time to apply the Taylor series expansion method. Okay, so just keep it as it is. Okay, and we will jump to next medium. The next medium is good conductor. Okay, the next medium is a good conductor. Okay, so for the good conductor, the conductivity is approximately, or ideally it is infinity, epsilon is epsilon 0 epsilon r, mu is equals to mu 0 mu r. Okay, so now the next question is, explain electromagnetic wave propagation in good conductor. Okay, so now it's an important question, has a exam point of view. The question is asked in this way: explain electromagnetic wave propagation in good conductor, or what is skin effect. Okay, explain it, or what is skin depth, derive the equation of skin depth. Okay, so it's a very important question, electromagnetic wave propagation in good conductor. Okay, so the fourth medium is good conductor. And which are the properties for the good conductor? We know that for the good conductor, sigma is infinity, epsilon is equals to epsilon 0 epsilon r, mu is equals to mu 0 mu r. Again you have to write these two equation. Okay, then do the calculation for this propagation constant. Okay, now let us start to do the calculation for propagation constant. Okay, so for good conductor, now we write it equation sigma plus j omega epsilon. Okay, so now here sigma is infinity. Okay, so you can say that sigma is equals to infinity. So here sigma plus j omega epsilon, sigma is equals to infinity. So sigma term is very very high compared to j omega epsilon. Okay, so you may write j omega mu sigma, because you can neglect plus j omega epsilon term, because ideally we have to take sigma is very very high, but it's infinity. Okay, so what is propagation constant gamma? Propagation constant gamma is alpha plus j beta is equals to j omega mu sigma. Compare real part and imaginary part. It's not possible. Why? Because here j term is present in a square root, so you cannot compare it. Okay, if it is outside of the square root, so you can easily compare, but j term, imaginary term, is present inside of the square root, so you cannot compare it. Okay, so first of all we have to solve this one. Okay, so alpha plus j beta is equals to, now I have to write it, I have to write this one has a polar form. Okay, so here it is under root of omega mu sigma, this one is the magnitude, and what is the angle? J, angle of j is 90 degree, but it is under root. Okay, so when the angle it is in under root, so it is a half. Okay, so angle is 45 degree. Clear? Okay, now okay, again see, because it's a new thing, this one. Okay. See here, suppose let us say it is z is equals to x plus iy. So what is mode z? Mode of z is under root of x square plus y square. And what is the angle of z? It's very easy. Angle of z is tan inverse y by x. Okay, it is the angle of z. Okay, but if z is equals to under root of x plus iy, then what is mode z? What is mode z? Okay, so in this case the mode z is under root of x square plus y square. And what is angle of z? Angle of z is under root of tan inverse y by x. Okay, and remember one thing, if angle is in the square root, okay, suppose 30 degree angle, square root, so answer is 30 degree divided by 2, so answer is 50 degree. Okay, always and always. Suppose it is 90 degree, but it is 1 by 3. Okay, so it is 90 degree divided by 3, so it is 30 degree. Clear? So in this way, tan inverse y by x, so it is nothing but tan inverse y by x divided by 2. So angle is totally half. Okay, so in this case, the same case, if x is 0, put here x is 0. Okay, so here x is 0. Okay, so this under root of y square, so this only under root of y. Okay, here x is 0, so y by 0, infinity, tan inverse infinity, 90 degree by 2, so it is 45 degree. Okay, so that is why I have to write omega mu sigma. Okay, so this omega mu sigma angle 45 degree. Clear? Okay, so alpha plus j beta is equals to under root omega mu sigma 45 degree. You can write as an exponential series, so this e raised to j 45 degree, you can write in this way. Okay, under root of omega mu sigma, it is e raised to j theta. Okay, e raised to j theta cos theta plus j sin theta, so it is cos 45 degree plus j sin 45 degree. Okay, cos 45 degree 1 by root 2, sin 45 degree 1 by root 2. So you may write omega mu sigma by 2 plus j omega mu sigma by 2. It is nothing but my alpha plus j beta. Okay, so now you can compare real part and imaginary part. Why? Because j is outside of this square root. Okay, so what is the value of alpha? Alpha is put here, omega is equals to 2 pi f, so 2 to cancel out, so this pi f mu sigma, and beta is also pi f mu sigma. So value of attenuation constant and value of phase constant both are same, which is under root of pi f mu sigma. So you can notice attenuation is present. Why attenuation is present? Because this one, because the conductivity is not 0, conductivity is infinity, so that is why the attenuation is present. So the attenuation constant is under root of pi f mu sigma. So attenuation is depend on what? Attenuation is depend on conductivity of the medium or the material and the frequency of electromagnetic wave. So if material offers very high conductivity, so it has a very high attenuation. So we can say that electromagnetic wave cannot propagate throughout the good conductor. So inside the good conductor, electromagnetic wave is totally 0. Ideally, electromagnetic wave inside the good conductor is 0. Okay, and beta is equals to under root of pi f mu sigma. Okay, so it is a very small calculation for propagation constant for good conductor, for the good conductor. Clear? Now next one is definition of skin effect, or what is skin depth. Okay, so skin effect and skin depth topic are already included in good conductor. So if the question is asked, explain electromagnetic wave propagation in good conductor, so you have to write all those things. Okay, you have to write the skin effect and skin depth also. Okay, so we have to stop alpha is equals to under root of pi f mu sigma. Okay, now skin effect or skin depth. Okay, skin depth. Skin depth. Okay, so word is say that skin means our human body skin, it is known as skin. Depth means the distance which is traveled by electromagnetic wave. Okay, so to understand this, I will draw here, suppose this one is a human body. Okay, this one is human body, and this medium is air medium, is a air medium. For example, consider it's a air medium and it's a human body, because human body is a good conductor. Okay, now electromagnetic wave is propagate. Okay, it's traveling here. Okay, so now for example, suppose electromagnetic wave is traveling through the air. I consider only one wave. You can consider electric wave or magnetic wave. Here I consider only electric wave. when it is entering the other phase difference, okay, now it is 0. You may notice it is 0. Okay, so suppose at the free space this value is E0, but when this wave is entering into the human body, this maximum value is decreased. The maximum value is decreased. Okay, let us consider one more case so you can easily understand it. Again, it is a human body, okay, and here it is the electromagnetic wave. Okay, suppose we consider the value of electromagnetic wave, value of E0 is 100 volt per meter. Okay, let us take one example. This value is 100 volt per meter in free space. For just example, I have to take 100 volt per meter. When it entering here at the surface, at this boundary, is the same value 100 volt per meter. When it entering, so suppose here the value is 50 volt per meter. Okay, and here the value is 33 volt per meter, and here it is 5 volt per meter, and after it is 0. After it is 0. Okay, that means the value of electromagnetic wave inside the human body is totally 0. That means electromagnetic wave is now never passed through the human body. Okay, or good conductor generally. So now the definition of skin depth. Okay, so how can we define skin depth? Skin depth means the distance traveled by electromagnetic wave inside good conductor where its amplitude becomes 33% of its maximum amplitude. Okay, so here is 100 volt per meter, now it becomes 33 volt per meter. So whatever the distance, this distance traveled by electromagnetic wave inside the human body or inside the good conductor, so it is known as, this distance is known as skin depth. Okay, and skin depth is denoted as del. Okay, this delta or del, you can say anything. Okay, so it's a delta is a skin depth. Okay, so again, what is skin depth? Skin depth means the distance traveled by electromagnetic wave inside the good conductor where its value becomes 33% of its maximum value. Okay, so it is skin depth. Okay, now so it is a function of time or space. It is a function of space. Space means it is a function of distance. Okay, so we take either electric wave or magnetic wave. Suppose I will take a electric wave which is a function of z. Z is a distance or space, which is E0 e raised to minus alpha z. Okay, so here what is E0? E0 is the maximum value. Okay, in this example I will take this 100 which is E0. Okay, now what is the definition of skin depth? Skin depth means the distance traveled by electromagnetic wave inside the good conductor value becomes 33% of its maximum value. Okay, so 33%, so here this value becomes 33%, so it is 0.33. maximum value is E0 is equals to E0 e raised to minus alpha z. What is z? Z is this distance traveled by electromagnetic wave inside this good conductor. E0 is cancel out, so it is 0.33 is equals to e raised to minus alpha z. So e raised to alpha z is equals to 0.33. Okay, so alpha z is equals to ln 0.33. So ln 0.33, if you solve using calculator, so it is approximately 1. So alpha z is equals to 1. So what is z? Z is equals to 1 by alpha. So z is equals to, what is alpha? Alpha is attenuation constant that we have already derived. Alpha is equals to under root of pi f mu sigma. Okay, so alpha is 1 upon under root of pi f mu sigma. So what is Z? The Z is nothing but the distance traveled by electromagnetic wave inside the good conductor, where its amplitude becomes the 33% of its maximum amplitude. And here we have to denote it using this sign, del sign. Okay, so del is equals to 1 upon under root of pi f mu sigma. Okay, so it is the equation of skin depth, and this effect is known as skin effect. Okay, this effect is known as a skin effect. Okay, so skin depth is depend on which parameter? Skin depth is depend on pi? No, because pi is constant. Okay, we know that pi is a constant, 3.14. It depends on mu. Mu is permeability. Okay, permeability of the conductor. Sigma, conductivity of medium. Okay, or the conductivity of this good conductor. And F. What is F? F is frequency of electromagnetic wave. Okay, F is frequency of electromagnetic wave. Okay, so you cannot change the value of pi. You cannot change the value of mu. You cannot change the value of sigma because it is a property of medium. Okay, so we have to change the frequency of our electromagnetic wave always. Okay, so if low frequency, that means higher skin depth, and for high and high frequency, skin depth is minimized. Okay, clear? So we have to write this topic skin depth in electromagnetic wave propagation in good conductor topic. Okay, so here we have to derive propagation constant. From the propagation constant you have to derive value of or the equation of alpha and beta, and from alpha, okay, then after we will discuss about the skin depth. Okay, now one more thing is left, and it is known as intrinsic impedance for good conductor. Okay, we know that intrinsic impedance eta is equals to under root of j omega mu upon sigma plus j omega epsilon. Okay, so for good conductor, sigma is very high, so this under root of j omega mu upon sigma. Okay, so eta is equals to, again I have to write it, j omega mu upon sigma. Again here imaginary term is inside the square root. Okay, so again how can we solve it? So this omega mu sigma angle 45 degree. Okay, so eta is e raised to j 45 degree. E raised to j 45 degree means it is cos 45 degree plus j sin 45 degree. Cos 45 degree 1 by root 2 plus j sin 45 degree is also 1 by root 2. Okay, so we can write omega mu by 2 sigma plus j omega mu by 2 sigma, but omega is equal to 2 pi f. Okay, so this pi f mu by sigma plus j pi f mu by sigma. Okay, so this intrinsic impedance has also two parts, real part and imaginary part. Okay, so that means, okay, intrinsic impedance has a real part and imaginary part. So what it indicates actually, see here, for example, okay, just for knowledge, for example, suppose if you calculate all those things and pi f under root of pi f mu sigma, okay, you may get the value of 1. So pi f mu sigma 1. Okay, so it is 1 plus j into 1. So it is 1 plus j, for example. Okay, I will just take one example. So it is 1 plus j. So intrinsic impedance is 1 plus j. What do you mean by intrinsic impedance 1 plus j? So it is mode of intrinsic impedance is under root of 2 and angle is 45 degree. Okay, what it means, but we know that E is equals to, E is equals to eta h. So what? So E is equals to eta, okay, value of electric field intensity is root 2 times higher than h, and the phase difference between electric wave and magnetic wave is 45 degree. Okay, that means we have observed phase difference between these two waves, We have to observe the phase difference between these two waves due to this intrinsic impedance. Okay, we have to observe the phase difference between these two waves, electric wave and magnetic wave, due to this angle, 45-degree angle. Okay, so there is a phase difference between E and H due to this intrinsic impedance. Here, phase constant is a different thing. Okay, but this one is the actual phase difference. It's a phase difference. Okay, here alpha and J beta. Here alpha value is under root of pi f mu sigma, and beta is also under root of pi f mu sigma. From this phase constant, what we have to derive? We have to derive the velocity of electromagnetic wave in medium. Okay, either the velocity is higher than the velocity of light, or it is exactly equal to the velocity of light, or it is less than the velocity of light. That we have to derive using this phase constant. Okay, but what is the phase difference between electric field and magnetic field? That we will derive using this intrinsic impedance. Okay, so here we have to finish the electromagnetic wave propagation in 4 different medium. First is electromagnetic wave propagation in free space, then lossless dielectric medium, then lossy dielectric medium, and finally it is good conductor. Okay, so in next lecture we will discuss about Poynting vector. Poynting vector means how much power is carried by electromagnetic wave. Okay, thank you.